Welcome to example 14. It's a similar problem to example number 13 that involves a work done by friction and different energies of kinetic energy and potential energy, except this is all symbolic now. In B part, you can then substitute the numbers in. So we're really going to concentrate on part A. We're asked to determine an expression for the distance d that this block would go up in terms of the initial velocity v0, the coefficient of friction, kinetic friction, and the angle of the incline. You'll notice there's no mass in there, and it's probably because the mass of this block cancels out. Okay, so the block slides upwards and eventually comes to a halt at this distance d. So the final velocity of this block is 0. So there are a number of approaches to solve this problem. You could follow again a dynamics approach, but let's try to concentrate on an effort that involves energy. I'll show you the dynamics approach at the end. Okay, we're going to utilize an idea that as it slides up, there is some energy loss due to friction. So the work done by the friction is equal to the change in energy of the crate. It's equal to the final energy of the crate minus the initial energy of the crate. Now, the final energy of the crate, when it gets to the very top, is just really potential energy, which is mgh. The initial energy of the crate, we'll assume, is just kinetic energy, 1/2 mv0 squared. Okay, so let's talk about the left side of this expression here. Let's do that over here. The work done by friction can be calculated by using the work formula. That would be the force of friction, which is constant throughout this whole process, times the displacement, delta r, times the cosine of the angle between the force of friction and the displacement, which would be 180 degrees. I didn't want to put in theta in here because that's the angle of the incline here. Let's elaborate on this, and we need to find the force of friction. So let's draw a free body diagram for this block here. So you should hopefully recognize that we'll have three forces acting on this. We have the force of gravity acting downwards, we have the normal force acting perpendicular to the surface, and we have friction going down the inclined plane because it's sliding up the inclined plane. And as it slides up, there is an acceleration that is going down the ramp A. And this angle right in here between FG and the line that is right along the normal force here is theta. So the reason why we have an angle of 180 degrees is because the displacement is straight up the ramp and the force of friction is straight down the ramp, and the angle between those two vectors is 180 degrees. So we have the force of friction times the displacement. Let's replace delta r with really d, because that's the displacement in our diagram, and then as this problem indicates. And this is times -1. So we have a negative force of friction times the distance d. So we now need to get rid of the force of friction. So we will have to look at the summing the forces here. The force of the friction is equal to the coefficient of friction that's given, so we have mu here, times the normal force times d. So we do have to get rid of the normal force here. The normal force is equal to, well, where's that? Well, that comes from the sum of the forces along the y-axis, which is 0. So along this y-axis here, the normal force is counterbalanced by the y component of Fg, so minus Fgy, and this is all equal to 0. So the normal force is equal to mg times, well, this adjacent side is cosine theta. So let's replace that into our expression here. We have negative mu mg cosine theta times d. I suppose we could put the d in here in front of it. So we have mu mg d cosine theta. So now we have this side determined, so we can replace that in here and write negative mu mg d cosine theta. And now we need to find out what the distance d is equal to. We're almost actually done here, but I do realize, looking at this expression, I see a couple things here. I see that there's an m in every term, So they can cancel out. But I also notice that there's an h in here, and we really don't want to have an h in our final expression. So we do need to get rid of this h. That h is this little height h that goes up. So if you see this triangle in here, DH, and then this angle here is theta. So we can write here that we know that sine theta is equal to h over d. So h can be replaced with d sine theta in the above expression. So let me just move down here where I have a little bit more room and rewrite this expression. I have negative mu g d cosine theta equals g times h, which we're going to replace with d sine theta, minus 1/2 v0 squared. We're trying to solve for d here, and we have another d, so let's bring these two terms together on the same side. So let's put them on the right side. We have g d sine theta plus mu g d cosine theta, and let's take this term and put it on the other side. We have 1/2 v0 squared. Now we could pull out some like terms out here. We have g and d, and then in the brackets here sine theta plus mu cosine theta, and this is equal to 1/2 v0 squared. So now we can solve for d here. It would be equal to v0 squared, and on the bottom we have that 2 from the half, and then we have g and then bracket sine theta plus mu cosine theta. And that's your final expression for the distance that it would travel up in terms of the initial velocity, the acceleration due to gravity, and the angle of the incline, and the coefficient of kinetic friction. So you can go into part B now and substitute these numbers in here and then quickly find the answer for the distance d. I'm not going to go ahead and do that because I've done the hard part. The easy part is just subbing numbers in. And that's it for this example. I can show you, just as a little side, to show you how to solve this problem using kinematics, and I'll just do that now. So as an aside, let's show you just a different way of doing this. You could use the equation that relates the final speed squared with the initial speed squared plus 2a and the displacement delta x. But the displacement in this case is d, so this could be v squared equals v0 squared, then minus 2ad. Now the reason I'm putting the minus sign in here is because if you refer back to the earlier diagram, the displacement is up, but the acceleration is in the opposite direction. So really, if I make my x-axis going upwards and make my displacement positive, then my acceleration is in the negative direction a there. So then we know that the final speed is 0. So we have v0 squared equals 2ad. So then, to solve for d, we would have the initial speed squared divided by 2 times the acceleration. Well, how are you going to figure out the acceleration? That's where you go back to your dynamics. So you look back at the free body diagram and you sum the forces along the x direction, and you'll see that there's a force of friction plus mg sine theta. So I'll just write it over here so you can see the diagram. You have sum of the forces equals ma, and then in the x direction you have the force of friction plus the x component of the weight, which is equal to mg sine theta, and then ma. So we have then mu fn plus mg sine theta equals ma. We can replace the normal force, what we figured out before, is mg cosine theta. So we have mu mg cosine theta plus mg sine theta equals ma. And you'll notice that there's an m in every term. And so now you have the acceleration, which is equal to mu times g times cosine theta. So we can replace that into here. We have velocity initial squared divided by this whole expression, which is mu g cosine theta plus g sine theta, and that is exactly the same expression as that over there. Although, yeah, I'm missing my 2 in front of here. Now I have the same expression. Okay, that's it. So you see 2 different ways of solving problems with inclined plane.